thrilled to introduce Dan Goldman, a professor of physics at Georgia Tech, who's giving today's physics colloquium. So Dan received his PhD from UT Austin in 2002. Back then he was studying nonlinear dynamics of granular materials. And I've actually known Dan since that time because he worked on really exciting problems on pattern formation in granular media. And then after the PhD, he went into something completely different. He worked on biomechanics at Berkeley. And as a faculty member at Georgia Tech, he was able to combine both biomechanics and studies of granular materials. And in fact, what impressed me most is that Dan invented a new field and just decided to call it robophysics. And most of us at the APS didn't know what to do with it. He persisted, and there are now sessions on robophysics. They have been sessions on robophysics for a number of years at the APS March meeting, and essentially it's about introducing robot experiments and simulations and models as new pathways to study emergent phenomena. So Dan is a fellow of the APS, PKs and Arthur Young Investigator Awardee, and we're looking forward to his talk on surprises in self-deforming systems.
Thank you very much, and I appreciate the introduction. Unfortunately, Dan can't figure out how to go full screen. So can anyone help?
So we have to switch to a Chromebook because the laptop failed.
Next to the X.
Yeah, what's the full screen command? Let's see. Full screen.
The button next to the X. Is that?
No, that's the opposite.
F11.
Yeah, try F11. Maybe it's function F11. No. Oh, okay, good. And we may want to turn down the light just a little bit if possible, but it looks all right to me. And now the flame will be, does my laser pointer show up?
No, it doesn't show up.
There it shows up. There it is. And then the claim will advance. But okay, so thank you all for coming. I'm Dan Goldman, and thanks for the introduction. And I'm going to tell you today about some, what I'm going to call particularly surprises in self-deforming systems. And if some of the videos or images are not good quality, it's because I'm broadcasting this from my computer in Atlanta because my laptop charging port died. So, fingers crossed that everything works. And thank you all for putting up with me and all that help. So I'm going to tell you today, very broadly, what I think is a very interesting, and I'll say, new class of systems that we in physics can study. And by studying, not only discover interesting dynamics, but make contributions to biology and engineering. And these are the kind of things I'm going to try to tell you today. This is a video by the time you're done. I hope you'll appreciate this is basically a brainless robot navigating and solving a relatively complex environment with no closed loop control at all, due to some surprises discovered in self-deforming systems. Okay, now, clicker is not working. That's okay. Maybe I have to plug it here. Okay, well, these are people. Oh, it's working now. These are the people that have done the work. Here's the thanks and credit. It's a pretty diverse group of folks, and disciplinarily, I mean, a lot of folks are now faculty members at different places who were graduate students, a mix of biology, physics, engineering, mathematics, etc. Lots more people, but these are the main players in our story today. I'll try to narrate them as I go along. Okay, I just figured I would give a little bit of an introduction. Much of my lab is studying living systems that function well. And I put well in parentheses, sometimes they don't function so well, but largely I guess they try to in complex environments. Systems like a little lizard that swims in sand, it's called a sandfish lizard, and when scared in the deserts of North Africa, or in a video in my laboratory, it dives in the sand and generates a wave of body bending that propels it through the granular medium. This is an X-ray imaging. We've been recently, the last 2 years I should say, studying interesting problems in growth and development, which in this case is due to an example of a plant root as it's growing through a clear gel medium Now we can watch, not only at the behavioral level, but beginning to at the cellular level, how these processes at the cellular level allow this plant to do interesting behaviors to find its way through complex environments. And we also spent a good bit of time studying collectives of organisms. In this case, a collective of ants, fire ants in particular, as they try to navigate a very complex, crowded environment of their own devising, a little tunnel. We like to model things as well. Here's a computer model, a simulation model, in which we've made a virtual sandfish. Here is this red thing, is a bunch of motors in a computer simulation that basically drive a wave of body bending down this simulated sandfish, and it's immersed in a medium of granular material, 300,000 particles, and where the particles are lining up, basically that's where they're moving faster. So this gives us a called discrete element method model of the movement of a sand swimming lizard in a granular material, and you can see how it self-generates a little fluid that it propels itself through. And finally, we like to do some modeling with the form of analytics, or resistant force theory, which you basically treat this wiggling organism or this wiggling simulation as a mathematical line, and as it translates, as each element translates through space, you compute the forces upon that, and then you simply sum the forces over the body. I'm going to expand on this a little bit to develop an expression for the net velocity of the organism as a function of the speed of a wave that propagates down its body. And this is a calculation showing the length. That's sort of the broad theme of what we do, of the kind of things I'm going to talk about today. Now, like I said, we spent a lot of time not only doing careful biological experiments, but trying to develop models to understand and look for broad guiding principles across diversity of systems. And there's two broad approaches for our model. One is kind of a bottom-up approach. We can start with the complexity, like where every cell is at every instant in time, and then add all that stuff together to create the behavior at the highest level. Or we can start from the top down. We can specify high-level dynamics, like the bending of a little lizard over time, and try to understand dynamics and add detail as needed. Modeling, of course, locomotion. Modeling anything is nothing new. In terms of locomotion, let's say swimming, since the 1900s, the last century, there have been plenty of analytic approaches to modeling, going by resistant force theory, slender body thing, mass spring models, and these have been very useful for discovering broad comparative principles of locomotion. First, starting in the 1940s, and of course, continuing on into our era, computers have come to the rescue. One can now develop the kind of simulation I just showed you in great detail. You can use solve partial differential equations to study bird flapping or rotorcraft hovering. You can use discrete element methods of bending particles to try to understand the swimming of a lizard. These are fantastic, very accurate in principle, but also relatively slow. It takes a lot of time to simulate a box of granular material. Now, in the 2000s, biologists started to realize, I'll put this at the 2000s, this is my little cartoon sketch, started to realize that you could use robots, of which we now see a lot of in our videos on YouTube, to start to model organisms. In this kind of situation, you don't need to solve equations which govern the interaction of a robot with the environment. The robot is the interaction with the environment, but it had been hard to make controllable low-cost devices. Until now. It turns out about 15 years ago, my lab, we discovered 3D printers. And we discovered low-cost servo motors. Motors you could basically send a command and it'll tell the motor to go to a certain position at a certain time. And we discovered low-cost microcontrollers, which have now been packaged so you can plug into your computer program. And the combination of those has basically revolutionized how I think, and no joke, how I think about what we'll call physical modeling of these things. Here's an example. Here's a 3D printed shell surrounding 10 or so motors, which each motor is connected to the next motor in a chain, and you send a program that turns one motor at one time, another motor the next time, so you can generate waves, you can generate arbitrary patterns on this thing, and you can let it swim in a relatively complicated granular medium, right, which would be very challenging to model, and try to understand in this situation why this thing is getting stuck in its place as it starts to ruck up material around it. We call this robophysics because it's not how the engineers tend to treat their robots. For us, the robot is the experiment, is the either experiment to try to understand the living system or the experiment just to discover cool stuff, not as a demonstration of a control principle. We treat robots as experimental tools to test hypotheses and learn from. Here's a couple papers. Now, in the last 15 years, I guess because of these tools, because of where I am at Georgia Tech, and because of the brilliant students, these things have invaded my lab. I mean, I now get flooded with engineering students who want to go, I want to build a robot, because they all grew up in high school. Like kids in the 60s and 70s programming computers, they all make robots now in high school in their makerspaces. And so here's just a few examples of the kind of things that I'm not going to show you all today, but it's just a whole lot of fun. And not only my lab, they've invaded journal covers. Here's three of our robophysical models on the cover of prominent scientific journals, something I never thought I would see when I started this business, including PRL. If you're interested in this, this is a robophysical model that vibrates, and there's a Casimir-like force, a fluctuation-induced force, which allows the robot to move to and fro from a boundary. Kind of beautiful. As Wolfgang said, if you're really excited about robophysics, you can come to the happiest place on earth, March 16th through 21, Anaheim. It'll be the 10th annual robophysics focus session. And there's been 4 sessions times however many talks in the sessions, 13, 14, for the last 10 years running. And so we'll be there, and if you want to learn about this kind of stuff. Now, one key feature that our robots, robophysical models display is something interesting. Here's 3 examples: a sand swimmer, a centipede sort of thing, and a little low Reynolds number algae type swimmer. They all actively self-deform. Seems trivial now that I say it. The robot's body, limbs, changes shape upon my commands as a function of time. That's it, okay? And it's an extended body, and it's in contact with the environment. What could be so interesting about that? Non-trivial. Let me show you. I'm going to define self-deforming systems as internally driven, damped, extended objects. You could have something like an earthworm burrowing. You could have something like a neutrophil crawling through a collagen matrix. You could have something like a molecular motor walking on a microtubule. This all, I claim, falls in the class of self-deforming systems, extended systems. They don't necessarily have to move. Whoops. They don't necessarily have to move. You could just have conformational changes. This is how a ribosome works. Opens and closes, opens and closes. It reads genetic code. Is it the protein? These, by the way, you might say, well, this is what Duchenne did. You know, that's what he got a Nobel Prize for. He basically studied extended systems wiggling around. Except that Duchenne systems were largely polymer, and they were largely driven by fluctuations in the environment. Our systems, and the systems I'm interested in, are driven by internal dynamics. Turns out that's very different. Ours are explicitly non-equilibrium systems. So here's what I say. Self-deforming system. You got active elements. They use energy to do work. They generate internal forces or torques. You can control a shape or a torque. They can, if you're feeling engineering-y, or what I think physics can really sort of sink its teeth into, they can experience and sense environmental actions, interactions to do something. And this is kind of a generic picture. I have a shape or a configuration, I'll use these interchangeably, and a sequence of those things, and over some time, the system changes its shape in some way, and that's the rule you get to specify. Now, we are not the first people to work on self-deforming systems. Here's one of my favorite quotes. This is from a well-known physicist, Mr. Maxwell. There's a tradition at Trinity that when I was here, I discovered a method of throwing a cat so as not to light on its feet. And then I used to throw cats out the windows. I had to explain the proper object of research was to find how quick the cat would turn around. Then the proper method was to let the cat drop on the table or bed for about 2 inches. That even then, the cat lights on her feet. How's it do it? Well, this wasn't worked out until Mr. Murray in 1894 showed that basically Kitty is not using air resistance to turn around, but the cat is doing a sequence of shape changes which allow it to do a zero angular momentum turn, always land on its feet without pushing off anything. Now, that may not sound particularly interesting or deep, but these folks got interested in this kind of problem back in the 80s. And here's a very famous paper. They called it Gauge Kinematics of Deformable Bodies, treatment of motion of a deformable body, so body changes its shape over time. It requires a specification of axes, and so on and so forth. Then in terms of a gauge, structure, or shape of space, as the body may assume, want to make the net change in orientation of a body at angle length of 0 from a good, blah, blah, blah. It's basically generalizing what this observation of the cat is. Okay? And there's some great stuff here. They have a lot of cool language on the geometry of sequence, blah, blah, blah. I'm going to come back to this. We should show the rotation of a self-deforming body to be naturally expressed in purely geometric form in terms of a gauge potential over configuration space. Particle physics language. Okay? The idea is very simple, though. It's two spaces. One with the self-deformation control, the other real space translation or rotation. And their framework connects these two spaces. That's it. And there's a whole lot of beautiful mathematics which backs all this stuff up. Here is where they really went to town, again, building on work from engineers and theoretical physicists, some who may be in this room. The paper in the 80s, called Self-Propulsion at Low Reynolds Number. And again, it had this great abstract formulated problem of self-propulsion at low Reynolds number in terms of a gauge field over the space of shapes. The computation of this field is discussed and carried in some examples. Results in term maximally efficient infinitesimal swimming motions of spheres and circular cylinders. And they have other verbiage about this, which I won't read you to, but the key ingredient here is that swimming microorganisms live in a world without inertia. In the limit of 0 Reynolds number, the swimmer's path through the fluid is determined solely by the geometry of sequence of shapes it assumes, not by the rate at which it changes shape. And this class of systems is what they're gonna try to apply this idea to. And let me just give you a thumbnail sketch after I show you this video. Here's a spermatozoa oscillating its flagellum to swim through a fluid medium. And the cool thing about this, and the non-intuitive thing about this, is that when I first started looking at this stuff, you might think it looks like an eel. It sends a wave from tail to head, down the body, pushes against the fluid, the fluid pushes it back. This is explicitly not the case. If this eel stops self-deforming, it keeps moving, it glides for some time. If the spermatozoa stops self-deforming, it stops instantly, or nearly instantly. That's very different. Here's a little bit of formalism just to show you some diagrams. Here are the main players in this thing. You have a shape manifold, the spatial internal degrees of freedom. You have SE2 here, the space of 2G rigid body kinematics, which can be the body's center of mass and orientation. And the game here is that paths in this space lead to paths in this space. And they're connected by literally a matrix called the connection, which tells you if I make an infinitesimal self-deformation, I get an infinitesimal translation rotation. And your job is then to compute this matrix A, or the gauge field, is what they call it. Well, okay, here's just something which will come up for a few slides, I just want to say it. Here's one way you think about curvy sort of things. I can parameterize a curvy sort of swimmer by curvature as a function of arc length, and I can describe that, it turns out, as the sum of two modes, a sine and a cosine, and a sinusoidal time variation of those two modes. And so if I want to think about this thing moving, I basically think about steering this thing around in a configuration space, which is made of those configurations. Everybody get that? That's the sort of first key bit in this stuff. Okay? Two modes and time variation of those modes will lead to paths in this configuration space. Well then, what you do is you want to actually compute the translation rotation over one cycle. So you compute the velocities, integrate over time, which turns out to be equivalent of computing this A matrix, A dot times dt, which is the equivalent of computing this A matrix around a round trip path dot ds, or S is the arc length in this thing, which by Stokes' theorem is approximately, in this case I put approximate for technical reasons we can talk about, is the curl of this A matrix A. And if I'm interested in how far this thing will go translating in the x direction, I simply do a path, this path, I do either a line integral over this space, and where I go with the flow of the vector field, that means I'll have good displacement that I'm adding up, or I do a surface integral over this region, and where there's a large surface integral means I've integrated over a large positive region, let's say, and that should get me a large delta. That's the story, okay? That's the framework. Well, why am I telling you this? Because these guys were talking about infinitesimal motions of spermatozoa. As fascinating as that sounds, that's not my main interest, as you probably saw. Well, it turns out that what they discovered is much broader than that. That's the first sort of surprise I can tell you about. Purcell's famous paper called Like Low Reynolds Number, in which he narrates the weird world of low Reynolds number locomotion. It really is bizarre to us, right? We swim like eels. If I swim in the swimming pool and glide a little bit, I can swim and stop, I glide a little bit, and swim and glide. A bacterium does not do that. As soon as it stops wiggling, it stops moving. So it's continuously self-deforming to self-propel. Now, Purcell in this paper, he had a great idea. He says, you know, this is a typical bacterium, a typical speed, or a typical Reynolds number, very low. The distance it's going to coast after it turns off its molecular motors is 1/10 of an angstrom, and it's going to coast for 1/3 of a microsecond. It's nothing. To that bacteria, there's no history, right? Everything is instantaneous. Well, I have a very smart postdoc, and he said, okay, here's an idea. Let me do the calculation. Here's Stokes' dragon spherical organism. I can compute the velocity as a function of time once I stop self-deforming. And I can generate a characteristic coasting time, that's m over m. And he said this motivates a non-dimensional number called the coasting number. How long the locomotor coasts relative to the time between cycles. If this number is small, then basically, again, there's no history. You don't get any self-propulsion via glide. Everything is low. And it turns out for E. coli, again, it's 10 to the minus 5. And for even a little nematode worm, which we're going to come back to, it's about 10 to the minus 2. Okay. Turns out it's related to the Reynolds number. We can talk about that later by a ratio of the densities of the fluid to the body. But that's not the interesting bit. The interesting bit is the following. You can ask, what about coasting in a friction-dominated system? You can calculate, if I turn off these motors, what would the time be for the thing to come to rest? And the answer is the following. In these granular systems, I have to tell you, you have to believe me, that instead of viscosity, it's friction, which is dominating. Coulomb friction, which is dominating dynamics. Coulomb friction is rate independent. And when things are rate independent, this is a problem I give in physics 1, you can calculate the time it's going to take from initial velocity to come to exactly rest, not simply to coast 1 over velocity. And that's its initial velocity divided by u(g). And if you start plugging in numbers, this robot or a lizard is swimming at 10 centimeters a second, u is 0.2, you coast for about 0.05 seconds, and your cycle is this thing, and you end up with about t coast over t cycle is about 0.05, since your cycle is about 1 per second. So your number is tiny. So that means this thing comes to rest in a fraction of its body length, in a fraction of time of its cycling. Well, the cool thing is that we study a lot of different organisms. We're looking for broad principles. And so Bashi basically went and tried to apply this to everything he could find in our lab in the literature, and here's a little table. And most of these things, the coasting number is sub 1. Again, the history is not important for these things. So they're effectively operating in the world of the very, very tiny, the low Reynolds number. The interesting interpretation of frictional systems is that this basically turns into a ratio of inertial to frictional forces, for those who are experts. So it's like a Reynolds number, but for frictions. Well, you can then rinse and repeat this whole game that Wilczek and Shapiro brought in for low Reynolds number, but for organisms in friction-dominated systems. You could do a dimensionality reduction. You could take your organism, calculate curvature as a function of arc length. Here's curvature as a function of time and arc length, showing waves of curvature propagating down a body. You can decompose that in a way I won't tell you into so-called eigensnakes, 2 modes, which was a term invented for worms by Bialik and collaborators. And you can basically, if you project the dynamics into this space, you find that it's basically a circle traveling around on the projection of these 2 basically sinusoidal and cosinusoidal modes. So this organism you could think of as basically self-deforming in a circle in an abstract configuration space based on sine cosine. Okay? Well, you need an RFT, so the RFT I already told you, you need forces, and then you need drag forces, and you did a lot of measurements of these kind of things in granular material because we didn't have Stokes' law. And then you can do your RFT calculation, but you're not done, because you need to go to your gauge kinematics model, you need to get your configuration space, that's from this, that's these guys, you need your connection field, and then you need your, we call height functions, it's this curl. And then your job becomes, figure out locomotion displacement by integrating, let's say, over this curve, get the surface area, okay? And so the displacement after 1 cycle for this is going to be the integral of this guy ds, or the curlness over this area. So you can see where you enclose a large red region, you're going to move a lot displacement per cycle, and when you enclose more than that, you don't. Well, lo and behold, then we surveyed all of our critters, as a paper that just came out last year, and to some approximation, they all look like, when they're swimming in their environments, a circle in this configuration space. They're all low coasting number. And basically, if you look at their height functions, they all pick a circle which approximately encloses that maximal region. They're maximizing their vary phase over one cycle in their geometric phase. And it doesn't just apply to these swimmers, it applies to crazy looking sidewinders too, and legged systems too. And there's a whole diversity of systems that we can basically perform this dimensionality reduction. And because of these things are low coasting, use this machinery to say, oh, I know why they're moving like this, because they want to go the furthest they can per undulation cycle, and that's the path that's going to get them that far. The hypothesis, the biological hypothesis, the organisms target these waveforms, which we call templates for their good local properties. And if you really want to get fancy, you can start to then say, how should self-deforming robots move the best? Here's an example. You can drive a robot around in a configuration space like this. You can compute its height function at granular material, and you can plot the displacement goes per cycle as a function basically of the peak curvature on this thing. Let me amplify that. If I have a point here, that means I've gone around a small circle in this configuration space, and you can see I don't enclose a lot of red area, so my displacement is modest. If I get too big of a circle, I enclose a lot of red, but also a lot of black, and it's signed area, so they cancel out and my locomotion is diminished. And there's a sweet spot where if I sit basically here, I can enclose a goodly amount of this red area. And lo and behold, when I make the thing go, it swims quite beautifully. Okay. It then gives you, if you're interested in making robots that can change their shape, it gives you a prescription on how to drive it around the best. I know how to drive a car the best. You know, V equals omega R, I simply crank up omega, and then I worry about fuel efficiency and all that stuff. Now we have a way to say, here's how to drive a undulatory, a wiggling robot best. But, good. The terradynamic world is rarely homogeneous and isotropic. Here's one of those same robots trying to get to a more complex environment. It turns out the terradynamic environment, that's a word we came up with, you're tired of using terrestrial or whatever, so you have aerodynamic, hydrodynamic, terradynamic. It looks kind of like this, either a disaster site or nasty weeds in a field or yucky stuff in a drain pipe. And the key feature is that a self-deforming system will encounter heterogeneities and stochastic environmental forces, which resist its shape changes in self-propulsion, allow new obstacles to push against, we'll call affordances, and generates opportunity for feedback control. You try to maintain your shape or adopt something new. Biologically, such domains are dominated by the very small and the elongate. Systems like snakes with no limbs kind of crawl around in the grass. We don't even see them, they're so effective. Systems which are near and dear to my heart now, centipedes, basically are these elongate systems with many legs. They can't see very well with their photon-based sensing, but boy, they have excellent tactile sensing from their antennae and their limbs. And even the world of the tiny brain. So these little nematode worms are so much more sophisticated, 100 neurons for locomotor control, so much more sophisticated than our best robots that it's embarrassing. Okay? The world of the terradynamically complex, lots of heterogeneities, is dominated by these things. So we need new principles of biological locomotion. Well, I've been thinking on this idea for now over a decade. And the original inspiration came from condensed matter physics and nonlinear dynamics. So here's an environment. You have smooth sand, and you have clumps of stuff, heterogeneities, all that clutter. And here's what a physicist does. Takes that and turns it into a smooth board with an array of obstacles, and then puts a robophysical model inside it and sees what happens. The nice thing about these lattices are going to come up now for the rest of the talk, is that you have nice flexibility. I can vary, let's say the locomotor is length scale L, I can make L smaller than any distance between the lattice element, or I can make it comparable so that my elongate self-deforming system has to encounter multiple obstacles which can interfere with itself. And so I can tune all sorts of parameters to sight into control and understanding principles. Okay? Well, what happens? We start very simple, okay? Here's the very simple. It's a robot, a little physical model with some number of segments, 3D printed, some number of motors, which are serially connected, and these markers which allow us to track it well using cameras, track its position. And it turns out we put wheels on the belly because those wheels end up mimicking a kind of anisotropic drag that's important for swimming in these low coastal environments. So this is a swimming wheel robot. The control scheme, again, is the same thing. I'm going to vary each joint sinusoidally, which turns out to be the equivalent of driving this robot self-deformation pattern in a circle in this abstract configuration space. And here's what it looks like. It's quite beautiful. Again, it's low coasting, so if I turn off, if I seesaw motor function, the robot stops instantly. Okay, so everything is instantaneous and local. Okay, and this is the line tracks. This is what it would sort of look like. You can see a little bit that they're not particularly overlapping. That's because all the wheels are always slipping just a little bit. It's a swimmer. This is the key thing. All these systems we're studying are basically swimmers at the macro scale. So here's the next thing you do if you're a physicist. You start with one obstacle. Here's one obstacle. And there's the robot. And it hits that obstacle. And it doesn't know about the obstacle. Everything, once it hits, is simply via the mechanics. The robot is trying with its controller to maintain its self-deformation shape pattern, its circle in that configuration over time. And it's doing a very good job. It's a very strong motor. So what do you see? Well, you can measure. There's 3, there's posts. The robot hits and it scatters off at some angle. And here's what you can do. You can add these things up over time, and you get kind of a pre-distribution. You'll notice that here's the peg that it hit, and here's kind of ghost images of that peg. For those in optics, very clearly see you know what this looks like. Here's a probability distribution as a function of angle. Note that it's peaked around 0. It's like if you didn't know what was happening, it's like the robot went through the post, diffracted around the post. Okay. I'm calling this mechanical diffraction. Don't get angry yet about the word diffraction, because I'm going to try to convince you that that's in fact the right word and concept. Here's the importance of persistent collisions. This is the key ingredient. The robot doesn't stop trying to drive its self-deformation pattern, but it encounters a heterogeneity, and so something has to give, and what gives is it gets rotated a little bit. And that rotation, how much it scatters, depends on how long it spends grinding its head. If it grinds its head a long time, it gets reoriented, and then shoots off to the left or to the right. And particular phases on the posts make it scatter the most. If it's dead on, spends a lot of time, and eventually gets scattered off. If it just grazes, it just goes around and gets scattered. By the way, we first saw this, I happen to be teaching classical mechanics, and I've been telling the students, you can learn everything about collisions by conservation of momentum and energy. I said, oh, wait, I got none of those here. So what do I do? Well, what I do is we do experiments. Okay, well, here's the next experiment. You go from one post to many posts, okay? Again, this is physics. We're not very creative. And you have a spacing between these posts, and you have the same deformation scheme. And here's what it looks like. And it wanders. Again, there's no control here, in the sense that it's controlling the self-deformation pattern. It's still doing a circle in that configuration space. And then here's Parent-Schiebel. Now, Professor Parent-Schiebel, I provide at Montana State. This is what she used to do all day and night as a graduate student. Pick up robot, put it down. Pick up robot, put it down. Vary initial conditions. You only get a finite region of initial conditions before you get repetitions because it's a periodic system, but she tried to sample uniformly in that box. Pick it up, put it down. Sometimes it goes to the left, sometimes it goes to the right. It's quite deterministic. Depending on where you start it, you have a good idea if it's going to go to the left or the right. This little box of initial conditions, which I will do later. Yes?
Would simulation not let you do many more of these?
It does. Give me a second.
Okay.
It does, but we wouldn't discover simulation. I have a lot of thoughts about simulation, by the way, about why it's good and why it's not so good. But we can talk about that. Here's what happens when you do it many times and you record the trajectories over many times. On the left, I'm plotting the trajectory of the head. On the right, it's the sort of average midline. And what do you see? Well, for the students who are taking modern physics, what does it look like? It looks like a diffraction pattern. And in fact, that's what it looks like after you do 100 or 200 experiments. You see some scatters to the left, some scatters to the right, scatters down the middle. And here you can measure the scattering angle, and there it is. The robot only emerges at certain preferred preferred angles out this last. And I like this. Both matter and radiation present a remarkable duality of characters, and sometimes in the properties of waves, those are the particles. Now it's obvious that they cannot be a form of wave motion that was part of that. The two concepts are too different. Heisenberg never looked at self-deforming active extended systems. If you don't believe that, I got a snake to sell you. Actually, got a snake to show you. Here's a snake. Same snake I showed you before. Snake lives in an environment, which guess what? Is mainly sand. It has a little creosote brush in there where it'll encounter heterogeneity. Here's some tracks that it left in the night. We do these physics experiments. Set up a lattice. Let the snake run. 300 grads an entire summer to get basically about 200 trials or something like this where the snake went through. And what happens? This is the pattern. And it turns out if you bend this thing, you get a 5-peak diffraction pattern from the snake. And here's a model. Before I tell you the model, I have to tell you what Mr. Newton said. John Bush gave me this quote. Are not the rays of light passing by the edge inside the body bent several times backward and forward like the motion of an eel? And do not three contours and colored light on these? Actually, you call it snake. Turns out there's a cool biological story, which I don't have time to tell you, but basically when you watch these things go, they crumple. They're moving really fast. They're not coasting, but they're moving at a meter a second. So basically, the body just kind of crumples when it collides. And it turns out there's a beautiful bit of muscle physiology that says when an elongate organism, like a snake, is self-deforming, it's not doing it like our robots where you have a bunch of motors connected. It has basically muscle on either side of a flexible spinal cord. And it kind of alternates back and forth muscle that goes down the body. I'm just hand waving because we'll come back to it. If you put that dynamics into a very simple model with essentially no fitting parameters, out pops this kind of simulation. It buckles at preferred points, and that leads to at least a 3-peak diffraction pattern. So it's very general. In fact, it's very general, and I'm starting to call these to myself, and I'll announce it here. I'm starting to bring up Eddington's old word of waveable. So some of you may know this book, The Nature of the Physical World, 1928, and he says, light, we shall say, is an entity with the wave property of spreading out to fill the largest object glass and with the well-known properties of diffraction interference. Simultaneously, it's an entity with corpuscular or bullet property, expending its whole energy on every small target. We can scarcely describe such an entity as a wave or particle. Perhaps a compromise would better call it a waver. And no less than Weishaupt said he liked this word. Nobody uses it. I don't use these things. Of course, we know what waveables do. Here's a video from Brown University that I'm just going to quickly show you because I found it, their lecture demo. Here's a gentleman whose name I don't know showing an interference pattern from laser light. And now you fast forward ahead in the video and he does a single photon interference pattern from some number of slits. Let's fast forward a little bit. And over time, if you count enough photon events up, you get a beautiful diffraction pattern. And of course, you get the maximum at d sine theta equals m lambda, which everybody knows. So it says that in a waveable experiment, if I vary the spacing, characteristic spacing between two scattering elements, I should be able to vary the angle at which I'm observing things. So we did that, and we made these close together, and we made the slits far apart. And if you look at the distributions, you can see when they're close together, you get a very broad distribution of power, strong humps. And when they're very close, when they're very far apart, you basically get the single post scattering function, and the width is small. And you can basically say that this is a robot waveable uncertainty principle. If in this robot, in this self-deforming system, I localize where it is spatially, it responds by spreading out, increasing its momentum. Okay? And in fact, it gets even crazier because you might ask, what's the characteristic width of this distribution as a function of post spacing? And it goes like this, and this fit is basically front off refraction, one fitting parameter, big D. And that big D is how wiggly the magnitude of that circle of that configuration is. Cool. You get very interesting, novel, we'll say self-interference dynamics. The robot collides, sometimes it just goes straight through. This is a computer simulation. Sometimes it collides, but once you observe these dynamics, it goes off, whoop, a double bump, and sometimes it gets really crazy, again, all spontaneously and emergently, and it goes 1, 2, 3, 4, whoop, and you can even get in simulation for the right parameters, evanescent modes, where the thing just then travels along the lattice forever and ever. Keep that in mind. coming back in a few minutes. So, okay, again, in our program, 1, linear array. Now let's go to a lattice. What could go wrong? Well, oh no! Let's see if it plays. So you know what's going to go wrong. Oops. No, that went wrong. Okay. Here's one thing. Oh, you get stuck a lot. You can't satisfy the constraints anymore. When you're trying to keep in this circle and configuration space, you spend a lot of time getting jammed up. Obvious thing, an engineering solution with engineers I work with is to soften the robot. Oops, it's not playing, having trouble. And if you were to see this thing playing, you would find a beautiful engineering solution which took thousands of lines of oops. Oh no, that was not. Which took thousands of lines of code and lots of sensors, high meeting controls, and lots of sensing to make this thing go through this lattice so nicely. Okay? It's slow and complex, sensitive to choice of these parameters. I'm not telling you about the scheme, about how it's responding and changing its shape dynamically, and we don't know why it works. We then look to these tiny brainless worms and find that they can move through rotten peach, again, with efficacy better than any of our robots can move through equally complex rheological environments. And they're adaptable. If you give them a lattice, they basically can scoot through. They can sort of resonantly transit from one spot to another. Quite impressive. And we sort of ask the question, does bilateral actuation play a role? Now this is sort of a little coded to talking, because I'm running to start a little late, I'm going to skip this and just tell you that the answer is yes. If you ask a question to talk, the rule is you always have to say yes, I think, right? And we developed a new kind of robophysical model which actuates bilaterally, either side of a flexible body, with cords and cables. And it looks like it shouldn't work. It does. You can then generate a parameter which is called G, which is how tight these cables are simultaneously on either side of the body. If G's 0, you can't bend it either way. If G's 0.5, it's hard to bend one way, easy to bend another way. And if G is very high, this don't matter what G is, it's very high, it's easy to bend both ways. This thing ends up with a kind of what we call directional compliance. It's like a force diode. It emits force in one direction and not the other. And it turns out you do that, and the damn thing, you turn it on, and it just goes. It solves basically any lattice. And it happens by this interesting force diode mechanism, 10 lines of code, no sensing, it just goes. Okay. Now, you put a skin on it, and it really just glides. So, again, when you have a model, you understand why it works. Okay. And it even agrees with biological data. So if I plot how fast this robot moves a function of its wave speed as a function of the post spacing of the medium, with no fitting parameters, essentially you get a model, a robophysical model that agrees with how the worms navigate. Okay. Well, again, I'm surrounded by engineers in my group, and they like to take things outside. You know, I would rather them stay as robophysical models in the laboratory, but they like to take things outside. And so here's what they did with this directionally compliant, and they even named things. They called this the mechanically intelligent limbless robot, Miller. They love to name these things, and it goes, and it just goes, and it solves. It does a computation which solves all these kind of complex constraints and just goes. And in recent years, students have taken even more of our robophysical models outdoors, and they become incredibly mobile to the point where we have science papers, other nice papers, basically show why, if you have this elongate self-deforming system with the right kind of called mechanical intelligence, you just turn it on and it goes over complex environments. It's becoming a real robot. Well, here's a brief little coda. A few years back, a longtime collaborator of mine, I got like 5 minutes, right? Yeah, good, 5 minutes, good. Longtime collaborator of mine, Philip Benfeed at Duke, said, you know, there's a plant biologist, said there's a major problem in agriculture. Pest, weed, fungus, etc. control is out of control. Weeds in a blueberry field in my picture, downy mildew from removing the extension. For weeds, especially crop fields, we have a decreasing effectiveness of herbicides. We have labor challenges. And automated solutions, there are robots out there which are going to go scout for weeds and try to kill them, are enormous and heavy, and they compact the hell out of the soil and they can't get into the tight spots you may want for your vineyard or your blueberry farm. What if a swarm of low-cost but robust robots get between a row, can autonomously search for weeds and other pests, 24/7 in control. This was Philip's idea. Philip sadly passed away last year, before he really got to see this stuff going. And look what's going. Here's my company. It's called Ground Control Robotics. We incorporated in 2021. Me, Philip, Daniel Soto was an undergrad, and now he was a master's student at Georgia Tech, and now he's employee one, and only. These other folks are fine people who, at Georgia Tech who kind of help us out. We have some business folks, and Eric, who's an undergrad, who's an art student, who turns out to be a whiz at graphic design. So if you go to our website, you can see beautiful videos, which actually looks like we're a professional company, which we are, because we're incorporated in Delaware. It turns out via seed funding, we've been able to make our robophysical models actually do pretty interesting things in the laboratory. Like just crazy things that you wouldn't think to do, weird parallel parking maneuver. All, by the way, I should say, with this geometric phase is telling us how to control these things. It's crazy stuff. And we have a prototype. An MVP, they call it. Not the most valuable prototype, but a minimum viable prototype called Major Tom. Ground control. Here it is. It's wiggling around. Here's a geometric phase flip. Tells the optimal way to flip over. All this stuff. Low coasting geometric phase. If we make any money, we get the thing. That's what it tears weeds out the ground. It just goes and goes and goes. If you're interested why it just goes with these many legs, this is our science paper from last year. It's a really cool story that has a connection to Shannon's communication theory of how you can send a message down the working channel. Okay. So the field experiments then said, man, enough of this regular lattice stuff, we got to start studying irregular lattices. So we did. And we started finding fun dynamics. Here's the robot doing some fun backscattering. Here's the robot in a really random environment, getting stuck, kind of localized in space. That was confusing to us. What can we say about where the robot will go and average after a long time? Well, here's where we decided to start with simulation. Normally I don't like to start with simulation, but we decided this time. Here's a robot, the details don't matter. Here's the kind of lattices you can create. A triangular lattice, and then we can create a random lattice, perturbing the centers of each post by some amount to create various ends. Okay? And here's what it looks like. For 0, the robot just runs through these. We set the wavelength of the robot to be basically half that of the spacing. So it can resonantly run, it's a beautiful dynamics, can resonantly run through the lattices. Here's when the lattice is slightly disordered. You see the robot, oops, kind of going around and getting kind of kicked around. And here the robot is kind of just swiggling around, going nowhere on average. It always finds a lattice vector and transits for any fine lengths. He transits along the lattice vector, reorients. The patient transits may be localized to reach a few lattice constants. And here's what a bunch of trajectories look like, starting from a bunch of different conditions. Straight runs, kind of diffusive like scattering, and then basically stuck in one place. Okay. Here's the statistics of our robot trajectories. I can compute R, the characteristic distance, the distance it goes after some time, and I can plot R squared as a function of time. And you know, this looks like slope 2, indicating ballistic motion. This is slope 1, sort of diffusive motion, and this is slope 0, really non-diffusive motion. Really subdiffusion motion. And one day I was looking and said, man, the ballistics, diffusive, so this really looks like the absence of diffusion in certain random lattices. Anyone get that joke? Okay. It turns out I was right. Okay, that was a joke. I was curious if that would land. It did not. Okay, chalk it up. It turns out that there's a nice paper from Phil Anderson, absence of diffusion in certain random lattices. He was talking about, of course, impurities of crystals causing disorder. And if you want to read about this, you can read my dear friend and colleague Andy Zimmerman's wonderful book about Phil Anderson, Minor Matter, Physics of Very Many, 4.7 stars. Not bad now. Now, the author, I just have to say, is a big fan of ground control robotics. And here he is. The author meets the robot. And he's laughing. Now, I'll tell you, not only does he have an interest in this, he has an interest in the last remaining few minutes I'm about to tell you. And this is where it gets kind of fun. Because it turns out that localization phenomena occur in many systems, right? Here's a nice Physics Today piece, 2009, 50 years of Anderson localization, observed diverse wave systems from quantum, disordered semiconductors, cold atoms, to classical, like microwaves, acoustic systems. And some of the nicest, I'll say, or most famous experiments in the last 20 years all folks know this, are from Bose-Einstein condensates, where, in fact, Alain Aspect and Lucio created Bose-Einstein condensates and let them run. And Aspect created disordered lattices in 1D. And Lucio basically took a page out of a very famous model called the Aubrey-Andre model in condensed matter physics, where you basically make a lattice. In these cases, these guys make a light lattice, and they put their Bose-Einstein constant in that light lattice, and they have one lattice of the wave vector k, and then they add a wave vector of incommensurate k, usually the Golden ratio, with a varying amplitude. So it's a way to make controlled disorder of these things. And when you do that, you get a transition in the spatial width. For low disorder, the cloud spreads out after some time, and for high disorder, it doesn't spread so very far. So we got excited. Said, let's see if we can see this with our waveforms. Now I'm going to close. So here it is. We use 3D printing boulder technology, which sounds like a joke, but it's awesome. Here's a boulder enmeshed in another boulder. Why do we do this? Because look at this. I can make a robot, which now doesn't have posts anymore. The posts were too rigid and straight. We have sort of a smooth gradation in force from these boulders. We can do a simulation again. And we can set a base boulder lattice of k as 2 pi over lambda over 2. And we heavy boulders of height 0.3 delta. This is just even big. And then you can add another lattice by 3D printing this one in and having an undergrad Dimitri over and over pick up the robot, put it down. Over and over pick up the robot, and change the lattice. And basically compute, watch how far this thing goes. And here's what we see. Here's the robot dynamics. It's 1D, there's constrained sidewalls, which make it so you can only go in 1D channel. So we're going to go 1D version, we're back to 1D. And you see it does a nice ballistic run. It resonantly finds this base lattice vector and just kind of runs along it. If I up the disorder, you'll see that it kind of gets there, but it sort of stutters on its way. And sometimes it gets kind of kicked back. And if you go even higher, it kind of gets frozen. Space. And then it gets better. You can track the position, you can measure the displacement over time. And here's displacement over time, ballistic. Kind of this interesting thing where you run and stick and run and stick and run and stick, and then basically stuck in place. And you can plot the average speed basically as a function of the perturbing lattice. And lo and behold, you get a transition at an intermediate disorder. And boy, does that look a lot like what you find in a Bose-Einstein constant. Okay? Now, it turns out that we have a theory for this. It's a spatially dependent resistant force theory, where basically that same resistant force theory I told you about earlier has now a spatial dependence. So a little simulated robot feels a force which is different periodically in this case as it moves through space. And here's what it looks like if it's a nice uniform force field. And here's what it looks like if it's a non-uniform force field. And you see that the thing just gets sort of frozen in space, rocking back and forth. And lo and behold, you get the same kind of transition in this model. Again, picking this incommensurate disorder. And the theory predicts a curve like this, which looks familiar. Remember, for beta is square root of 5 minus 1 over 2. And if I put a rational second lattice in there, I don't localize it. I have a perfectly nice running for all values of the second lattice magnitude. Do we see this in an experiment? Yes, we do. You can delocalize the robot in this lattice by making a second lattice which is rationally related to the first. And by the way, if you're really interested, you can play all the games that Aubrey-Andre play, and you can almost reproduce plot for plot of these things. Okay. Oh yes. Now, I was gonna tell you that actually you get exponential probability to find the robot, but I'm not gonna show you that, I'm just gonna tell you that, and invite you back for a longer seminar. But that's the next game we're starting to play, to actually look at the statistics of these things. But let me just conclude. Here's some surprises in self-deforming and self-propelling systems. Geometric phase is important in locomotion. It's not restricted to the microworld. Low-coasting systems are ubiquitous and elongate self-deforming animals and robots. Serpenoid, today, undulating robots that say act like active wavicles. the mechanically diffracted regular lattices. Modeling bilateral actuation of robot leads to a sort of forced diode mechanism and motivates the importance of mechanical intelligence to control self-propulsion. And disorder lattices, the Anderson-like localization robots, further evidence for the active wavical picture. We need, though, like the Jean did for polymers, we need a theory of these things, a very broad general theory. And I think the ingredients actually are probably to be found in aspects of physics from last century into this century. And I think they're important. And why do I think they're important? Because will this and a general theory lead to useful robots and make me a lot of money? Well, you know, it might be back in 10 years as you can see. So I'll close with that and take any questions, and thank you for listening and appreciate the patience.
Question or two for Dan?
Have you considered systems with multiple robots that interact with one another?
Yes. Yes.
And
That's a longer story, but the answer is that we study that in robots that are basically point robots, where you can sort of think of it as gas. But it turns out that we can get literally entangling robots in a collective to do very interesting things like form solids, active solids, gases, fluids, and sort of thing. That's not yet in this kind of stuff. So yeah.
So I appreciate that you got into studying this because you were interested in sort of undulatory movement through granular media, right?
Yeah.
Is that the sort of best robot to run around in the field?
Which one?
Well, I mean a robot that, you know, essentially looks like a snake and undulates through a field. Is that the best robot for what you want to do?
Yeah, it's a very good point. What is best? I can throw it back and say what's best. Here's what I will say you get advantage. You get a robot that's sort of like this, but really long with lots of legs. You get a small profile. If you can fit your head through, you can get in there. You get heft, you get mass, you get multiple segments, which allows you to potentially tug on things. You get redundancy. The point of this 2023 paper, the science paper, is that basically if I add enough limbs, even an open loop, I can guarantee I can get from A to B in a certain amount of time with a very increasingly small bounds on that time. That gives us a principle that says if I put this thing in a field with a certain bumpiness, a certain noisiness, I'll be able to transit an acre in a day or two or three. Then you might say, well, do you need all those legs? Right? Do you need that?
I wasn't going to say that.
What were you going to say? I'm curious. The answer is, we think it's a pretty good solution. Pretty good.
I have a question for you. Good talk. I remember last time we talked about serpentine motion and going up trees. How did that pan out for you? Because you talked about undulation with snakes and trying to have a snake go up a tree.
I don't think I talked about trees, going up trees. We haven't studied vertical.
You did talk about serpentine motion. But
Yeah.
have you looked into vertical motion?
No, but it's of interest. But other folks are looking into actually in the biological systems. A former postdoc of mine in Denver is now looking at climbing snakes.
Last question.
Dan, great talk. You kind of alluded to it at the end when you added compliance to your robots, but
Yeah.
one of the things that occurs to me for the biological systems, even at very low Reynolds numbers, is that they still are flexible bodies, so the structural dynamics seem like they might be valuable. So I'm curious if you've explored modeling them as elastic rods where the intrinsic curvature is their actuation, but there's a bending potential that arises due to these resistive forces.
Yes, we have, in fact, a couple students on that very line of research. And it's very interesting. It turns out that the important feature for these systems at low Reynolds number or low coasting number, right, very general, is really just a sequence of shapes over time if the environment is uniform and homogeneous. As soon as heterogeneities come into place, then this bit of compliance, directional compliance, whatever, even internal elasticity can have important roles, not only for maneuvering around heterogeneities, but also for load sharing among the actuators. And there's a longer answer to that, but the answer is we are. We've started with the sort of shape changing, because that's sort of where we thought some real progress, and now we're bringing in the physiology of the biology side, or the kind of more sophisticated internal mechanics of robots to solve particular tasks, save energy, help motors out, this kind of thing. Yeah, that's certainly of interest in it's as is other kind of closed loop sensing, by the way. I just didn't talk about that.
Thank you again.
My pleasure.